All right. I hope that it is audible to everyone. Yes. Okay. So, sorry for the audio disturbance. Fine. So, okay. The we were discussing about the moment of inertia, right? Let's continue with that. So, what are the theorems first? What are the theorems? And what are the moments of inertia of the standard geometries? Fine. We'll be discussing overall. Number one, rod. Fine. Number two, ring. Fine. Number three, disk. Fine. Number four, sphere. Fine. This sphere could be hollow, and it could be even which way? Could even be a solid sphere. Fine. So these are the discussions that we'll be having. All right. Okay. So now, what are the theorems that we'll use over here for all these moments of inertia? Basically, there are two theorems. Fine. Theorems of MI. Fine. One is the parallel axis theorem. Fine. The other one is the perpendicular axis theorem. Fine. So what does the parallel axis theorem state, and what is it useful for? First, we'll just state them, then we'll go to the proofs of them. Fine. So let's say that you have one object over here. Fine. This particular object, it has the center of mass over here, and this is the axis through the center of mass. Fine. Fine. And over here there is one more axis which is passing through some point over here, and this axis is parallel to that one. Its moment of inertia is I. Fine. This moment of inertia is nothing but, we'll call it as I comma. Fine. What's the relation between these two? The relation between these two I values is also known as the theorem of parallel axis. Fine. This I value is equal to I comma plus the mass of this object, full object, multiplied by the square of the distance between them. This is your what theorem this one is? Parallel axis. Why axes are parallel? One of them must be the center of mass axis. Fine. Second one, and this is valid for any type of object. It could be a planar object. It could be a non-planar object. Fine. Fine. Okay. Now, what's the perpendicular axis theorem? Now, this is only valid for planar objects. Fine. When we say planar, you can imagine what it means. Fine. It means, for example, all of the mass is present only on a plane, maybe the XY plane or the YZ or the ZX. Fine. So this states that, and planar objects are also known as pancake or lamina. Fine. So let's say that this is your axis over here, x-axis, y-axis. Fine. And this is the z-axis over here. Fine. This is the object which is in one of the planes. You can see that it's in the XY plane. Fine. So now this is valid for three mutually perpendicular axis. Fine. Two of them must be in plane, one of them is perpendicular. So For example, if you had, say, this particular point P over here, fine. Let's say that this is I1, fine. And I2 is this way, fine. The angle between these two is how much? 90 degrees. And these two lines are in the plane of the lamina. That means in the XY plane or the object's plane itself. And there is one more which is perpendicular to this plane. Fine. What is that? That will be this way over here. Fine. This is your I3. Fine. Make a note that I1, I2, I3 are mutually perpendicular. Two of them are in plane, one of them is perpendicular to the plane. What the relation between these three moments of inertia is known as the what theorem? Perpendicular axis theorem. Fine. So I3 is nothing but I1 plus what? I2. This is nothing but what? Perpendicular axis theorem. Fine. So what are the limitations for perpendicular axis theorem? Only for planar. Is there a limitation for parallel axis? No. Conditions are there. One must be for passing through the center of mass. For perpendicular axis, there is no condition like it has to pass through center of mass. Done. Done. Proof, we will take it up at a later point of time. Towards the end, or let's see. Fine. Okay, so now let's move on to the proofs, the derivations. Fine. What? Number one, rod. Fine. Rod it is. What kind? What is a rod? It's a thin rod. What do you mean by a thin rod is that it doesn't have a large area of cross section. Fine. It's thin it is. This way it is. Fine. And whose mass is given to us as equal to how much? M. Length over here is how much? L. This is the center mass. This is the axis. Fine. This one. And we want to find out the moment of inertia of this one about this axis. Fine. This is the element over here. Fine. So if this is the element, then what's the elemental moment of inertia? We notice that this distance over here, let's take that is equal to x. We are going to set the center of mass as the origin, x equal to 0. Over here at one end, it will be plus L by 2. And this one over here will be how much? Minus L by 2. Right? Right. So therefore, what is this particular distance over here? A small increase in x, which is dx. Fine. Then what is the value of di? Small or elemental moment of inertia. It is dm, mass of this one, multiplied by the square of the distance from the axis. And what is dm? Can we write this as equal to lambda, the linear mass density, multiplied by dx? Definitely. So you write lambda dx into x squared. Now you do integration. That's all. From where to where? The lowest possible value of x, from minus L by 2 to where? To plus L by 2. Okay. You can write lambda x power 3 by 3. From where to where? Minus L by 2 plus L by 2. What do you get? Lambda is what? Mass per unit length, right? Right, as m by L itself. And if you substitute over here, you take the 3 also outside. It becomes L cube by 8, right? Minus plus L cube by another 8. So what do you get? 1 by 8 plus 1 by 8, 1 by 4, 12. M L cube by L is L square. Fine. This is done. This is done for your MI about which axis? About the center of mass axis and perpendicular to the length of the rod. Fine. Now let's find out the MI about You have to remember this one. Okay. Now let's find out the moment of inertia about which axis? About an axis which is this way. This way. And passing through one end, and it is perpendicular to the length of the rod. Right? This I value we want to find. This one is okay. Now we are going after this one. Fine. So what do you write over here for this one? You can use elemental integration, and the limits will be from uh, 0 to L itself. That will give the answer. If you make the origin at the left hand, that's one way. Fine. Integral of lambda dx into x square from 0 to L itself. Or we can use the parallaxis theorem. What is the parallaxis theorem? This I is equal to I com plus mass into distance squared. So what is the distance between this axis and this axis over here? Is that half of L? Yes. Just use that. Easier it is. This is nothing but I com plus the mass into L by 2 the whole square. I com is how much? 1 by 12. What is this one? ML square by 4. Okay. So what do you get over here? You get this as 1 by 3 ml square. Fine. This is also done. And this short video, it is on these two proofs. Rest of them, give me a feedback how it is, and then we'll do the rest of them. Fine.